Today, I would like to discuss about how the force transfer works between the concrete and the rebar. Also, what is the difference between anchorage length, development length, and transfer length? There is a concrete block and reinforcement which is embedded into this concrete block. The tensile force T is applied at this part of the reinforcement. The force T has to be transferred to this concrete through bond resistance. That bond resistance is achieved by the development of tangential stress component along the interface between the rebar surface and surrounding concrete. This bond stress will be non-uniform and maximum at base of the concrete, and it will be zero at free end of the rebar. For the calculation purpose, we can assume that this bond stress as a uniform and average stress along the length of the rebar. So, how the bond stress achieved between this reinforcing surface and surrounding concrete? Due to hydration process, some chemical adhesion developed between the reinforcing surface and surrounding concrete. This chemical adhesion can be developed in both deformed bar as well as plain bar. The another factor is the frictional resistance. Due to surface roughness of this reinforcement and grip force created by the concrete shrinkage will create some frictional resistance. This frictional resistance can be developed in both deformed bar as well as the plain bar. The third important factor is the mechanical interlock. The ribs provided in the deformed bar will act as a mechanical interlock. If I cut this deformed bar and if I see the longitudinal section, it will look like something like this. When the force is applied in this direction, the surrounding concrete will create some reaction against each rib. So this mechanical interlock will be developed only in the deformed bar and it will not be developed in the plain bar. These are the factors will affect bond strength. The first one is the bar diameter. Since the bond stress is non-uniform at maximum at face of the concrete surface, larger the bar diameter, the stress will be more and concrete will fail. So it always better to have a more number of smaller dia bar rather than less number of larger dia bar. Another factor is concrete cover. Let us in a section something like this. If I have a rebar here, if the cover is more, the concrete can take more load before it crack. So, so the cover is more, the bond strength will be more. The another factor is spacing up rebar. The spacing up bar is less. Let us assume this is a bar 1 and this is bar 2. When this bar is loaded, the surrounding concrete will get stressed. So if these bars are placed very close, the stressed concrete may overlap and it will take less load. So it always better to have more spacing to get more bond strength. The another factor is the transverse reinforcement. If we have closed stirrups, it will provide a good confinement to the concrete and it will take more bond strength. And the another factor is grade of concrete. The higher the grade, it will have higher bond strength. And the location and position of the rebar. This we will discuss little later in the top bar effect. And the aggregate used in the concrete. Lightweight concrete required more bond length than the normal weight concrete. The another factor is coating applied on the reinforcement to reduce corrosion. So this will reduce the bonds and so we have to increase our bond length. And the another factor is the type of reinforcement. So the deformed bar will give more bond strength than the plain bar. So why this bond length sometimes called as anchorage length and development length and transfer length. Also why it is called as a length basically. So that bond strength is directly proportional to the surface area of the reinforcement which is directly conduct in concrete. So basically this is that area. So pi times diameter into length of the bar which is embedded into this concrete. Let's cut this and make as a planar section, something like this. So this is L and another dimension is pi d. For a given diameter of the bar, this pi d is always fixed. So if we require more bond strength, then we should have more length. If we require less bond strength, so this length should be less. So let us see a case where a stake cable anchor block. So some force or tension T is applied in this stake cable. That force T has to be transferred to this concrete block. So the bar length that must be present inside this concrete block to transfer the force successfully from this rebar to this concrete. So that length is called anchorage length, and the surrounding concrete is creating bond with this reinforcement. That bond is called anchorage bond. Let consider a case where simply supported beam with a point load at a midspan. So this point load may have a bending moment diagram something like this. The maximum moment at exactly under this point load and it will become zero at the support. So the tensile force in this reinforcement will be directly proportional to this bending moment diagram, and the maximum stress will be exactly under the load. And let's consider one more section somewhere either towards left or right to this peak point. Let's consider here. So let us assume the tensile force developed in this reinforcement, let's call it as a T, which is directly proportional to this moment. And here the tensile force developed in this point is, let us assume T plus del T. So the force T is balanced by T at section. This section is balanced by this tensile force, and the remaining component del T should be balanced by the bond stress developed between this reinforcement and surrounding concrete. So between these two sections, so this bond stress is called as the flexural bond. So the T will be equal to this T component, and this del T has to be taken care by the bond stress, the flexural bond between these two sections. So the minimum length of the bar on either side of this maximum stress point is called as a development length. Then why here we are calling it as a development length means here the resistance developed by both anchorage bond and flexural bond. In a previous case, the resistance is developed only by the anchorage bond. So wherever we have the flexural bond and anchorage bond, then we should call it as a development length. Otherwise, it is a anchorage length. Consider another case where a pretension beam. So there is a tendon. This tendon can be pulled with the help of jack. After that, the concrete will be poured and they leave the concrete to gain certain strength before releasing the jack. So when the tendon is pulled by this jack, the tensile force developed in this tendon will be uniform throughout its length between the jack. So once the jack is released, the stress in tendon becomes zero at this particular point. So after that, since the bond is developed between this tendon and surrounding concrete, it will started giving resistance. The resistance is added, keep on adding. So it will reach certain length to reach the effective stress. So the length from the end of the strand to the point where the effective stress is developed. So that length is called the transfer length. So till now what we have seen is what is bond length. Now we will take one example and we will see how to calculate this bond length. So to calculate the bond length, we should know the yield strength of the rebar and bond strength between bond strength developed by the concrete and a reinforcing surface. And to get the bond strength, we should know the bond stress. This bond stress, what is said from our Indian standards, and also what is top bar effect. So let's consider an example case where there is a support. Let's assume this is a wall or a column, and there is a cantilever beam of 5 meter length and zero point 0.3 meter by zero point 0.6 meter cross section, which is subjected to uniform distributed load of 5 kilonewton per meter length. So let's calculate a moment due to this external load. So the load is 5 meter into 5 meters. So the total load is 25 kilonewton, and which is going to act exactly at the mid, which means 2.5 meter from the support. So the total moment is 62.5 kilonewton meter. And moment due to self weight, let's assume a 25 kilonewton per cubic meter as a unit weight of concrete, and the cross section is 0.3 meter by zero point 0.6 meter per 1 meter length. So zero point 0.3 times zero point 0.6 into 25, so which is that unit weight of the 1 meter length beam, and the total length what we have is 5 meter. And the same as like the external load, this self weight also uniform load, so which will act as half of the span, so 5 by 2 meters. The total moment is 56.25 kilonewton meter. So let's consider a factor of 1.5 for both self weight as well as the external load. So the total moment is 178.125 kilonewton meter. Let's assume a bar diameter as a 20 mm and grade of bar is Fe500 deformed bar. Grade of concrete is M35 and cover is 50 mm. So the area of reinforcement required for the moment of 178.125 kilonewton meter is 823 mm square. So area of 120 mm bar is 314 mm square. So let's provide a 3 bar. The total area provided is 942 mm square. So the maximum stress in the rebar will be at the face of this support. So we should have enough bond strength left to this critical point. So to to be in equilibrium, the bond stress developed left to this critical point should be equal to the yield strength developed right side to this critical point in the rebar. So basically the bond strength should be equal to the yield strength. So this bond strength will be equal to the surface area of this reinforcement bar, which can create bond with the surrounding concrete and the bond stress. So which will be equal to the yield strength of the rebar. So the bond surface area should be equal to pi dl, and average bond stress should be equal to the cross sectional area of the rebar into yield stress or sometimes we can use actual stress also. Let's see, in this case the reinforcement required is 823 mm square. Since we provided 942 mm square, the ratio of these two will give the actual stress. So the yield strength should be equal to the cross-sectional area of the rebar into yield stress. So what is yield stress? When we test this rebar FE500 in UTM machines, we will get a stress strain graph something like this. So initially when we started loading the rebar, the stress and strain will vary linearly up to certain point. After that there will be sudden reduction in the stress. So this point is called yield strength, yield stress. And this yield stress into cross-sectional area will give the yield strength of the rebar. After this point, again it will start increasing the stress due to the strain hardening. It will reach the maximum point. After that the neck will start forming. After certain time this will be fractured. So the bar diameter is 20 mm, grade is Fe500, cross section area is 314. So the yield stress should be equal to the, yeah, since the grade is 500, so 500 divided by the partial safety factor for the steel is 1.15 as per IS 456. So the yield stress is 435 approximately, 435 megapascal. So the area into yield stress will give the yield strength. So the 20 bar can take 136.59 kilonewton before it start yielding. So the next is bond strength. So bond strength will be equal to the surface area of the rebar can create bond with surrounding concrete and bond stress. So how to get this bond stress? Either we have to do some laboratory test to get the bond stress of the particular grade of concrete, or we have to refer some standards like IS 456 or IRC 112. So let's see, in this case we will see what is said in IS 456 regarding the development length. So if you check the class 26.2.1 in IS 456, you can find this equation to calculate the development length. So this equation is just rearranging the equilibrium equation. So here the pi is there, pi is there. You just cut the pi and diameter of the bar, and so if I rearrange these things, this average bond stress we have to take to this side. So here the average bond stress they are using the notation of tau BD. So the dia bar into yield stress or actual stress divided by 4 times the bond stress. So the same equation we will get. So it's just that rearranging the equilibrium equations. In this table is the bond stress for the various grade of concrete is given for the plain bar and tension. For the M35 grade concrete, so 1.7 is the bond stress which is applicable for the plain bar and which can take the tension load. So, so for the deformed bar, the same IS 456 they have given that the bond strength whatever listed in this table for the plain bar can be enhanced by 60%. So also if suppose the bar, same deformed bar is provided for the compressive force, then again we can enhance 25%. So after correcting all these factor, in our case this 1.7 for the plain bar for M35 grade concrete, and that 60% enhancement for the deformed bar, that the final bond stress will be 2.72 for the tension bar. If in case of a compression bar, the value will be 1.7 into 1.6 into 1.25 for the compression. So the 3.4 megapascal we should use. Since we are calculating the development length for the deformed bar in tension, so our value should be die of the bar is 20 and 435 is the yield stress and 4 times the bond strength, which we calculated just now 2.72. So the total length of the bar should be present inside the concrete to develop this 136 kilonewton is 799 mm. So the load carrying capacity of the rebar should be minimum of the yield strength and the bond strength. If the LD provided is less than LD required, so the concrete will fail in bond failure before its yield. So this basically not recommended because this failure will be brittle in nature. It will happen in sudden without any warning. Suppose if the provided LD is greater than or equal to the LD required, then bar will fail by yielding, and it will give some, it will create a crack in the RCC element, so we will get some warning before it collapse. So it always prefer to design as a ductile element rather than brittle element. So that is why we should provide the LD should be at least equal to required or greater than required. It should not be less than required. How the force transfer works in lap joint. Let's consider a beam of span 20-meter length. Let's assume the 20 diameter bar is required from the start to end of the span for the particular load condition. So since the 20 meter is the span, in market we don't have the 20-meter length bar. So the maximum available length is the 12 meter. We should have at least one joint. In case of a mechanical joint, let us assume bar 1 is here and bar 2 is here. These two bars can directly connected with the help of coupler. So the force transfer will be directly from this bar to that bar through the coupler. So there is no force transfer here from the rebar to concrete and concrete to rebar. In case of a lap joint, if you see here, so here there is no bending involved since it is a support. Here we should have some anchorage should develop that bond strength should be equal to our yield strength. So the same in another support, we should have sufficient length inside the support to develop the bond strength. It should be equal to that bar yield strength of that particular bar. So in a lapping zone, we should lap the bar sufficient length so that that bond strength created at the lap joint should be equal to or greater than the yield strength of the connecting bar. Let's consider section 1. Section 2 and section 3. In section 1, the bar will have full yield capacity, and section 2 the bar 1 will have zero capacity. And if I see the rebar 2, it will have zero capacity at section 1 and full capacity at section 2. If I consider a section anywhere in between the section 1 and 2, let's say section 3, if the section 3 is exactly midway between these two sections, then the capacity of the bar 1 and bar 2 will be equal, and it will be equal to half of its yield capacity. So in between section 1 and 2, if I take section anywhere, the sum of the bar 1 and bar 2 will be equal to the total capacity of this particular 20 diameter bar. So here the force transfer is from bar 1, all the force transferred to the concrete in this particular zone, this lapping zone, and again from the force from this concrete transferred to the bar 2. So the forces are transferred from bar to concrete, concrete to bar. So that is how it works. Let's consider another case where a same beam of 20-meter length. So for another particular load condition where we will have the maximum bending moment at this zone, and beyond this point this 20 bar is no more required. So let's provide a 16 diameter bar beyond this point. So this is the zone for the 20 diameter bar, and behind that 16 is sufficient to take care of the bending moment. So since this 20 bar we should extend for the LD distance to have the sufficient anchorage on both the side. Same way we have to lap the another 60 diameter bar with a 20 diameter bar. So to calculate this lap length, whether should we consider the larger dia bar or the smaller dia bar by seeing this force diagram. Since our lap bond strength should be equal to the yield strength of that particular bar. So when we are lapping two different diameter bar, so considering the smaller diameter bar is sufficient for the lap length calculations. You no need to calculate for the larger dia bar. So in case of a bundled bar, when bars are contact each other, there will be some reduction in the contact area to create bond with surrounding concrete. So to account that reduction in area, we should increase the length. So in IS 456, so we have to increase the 10 percentage for two bars in contact, and 20 percentage for three bars in contact, and 33 percentage for the four bars in contact. So 799 is the development length required for one 20 diameter bar. If two 20 diameter bars are bundled, then we have to provide 879 as a development length. If three bars are provided in one bundle, then we have to provide 959 for the development length, and four bars are provided as a one single bundle, then we have to provide 1063 Now we will see how to calculate the development length as per IRC 112. So to calculate the development length, the same relationship what we have seen in IS 456 same only given in IRC 112 as well. So here these three factors, constant 4 and yield stress of the rebar and bond stress of the concrete put together, so they calling it as factor K. This value of K for different grade of concrete and steels are given in separate table format. So the value of K for favorable bond condition is given here. So for the various grade of concrete given here and various grade of steel is given here. The plain bar given separately and deformed bar is given separately here. So for in our case we are seeing M35 grade concrete and Fe 500 steel. So for that we have 36 as a K value. So 36 into 20, so 720 mm development length record for in case of the favorable bond condition. And for the unfavorable bond condition, we should be multiplied by this factor 1.43 to account the unfavorable bond condition. So in that case, we should provide 1029 mm as a development length. So now what is favorable bond condition and what is unfavorable bond conditions? If you see in IRC 112 code, they've given some image similar to this. Wherever the hatch is given, your reinforcement provided in the hatch zone, then you can take it as a favorable bond condition. When there is a no hatch in the reinforcement location, then we should be considered as a unfavorable bond conditions. To understand this favorable unfavorable bond condition in more detail, we should understand the what is top bar effect. The another factor which influences the bond strength is the depth of fresh concrete under the rebar during casting. If you see in the image, a lot of voids are there in the top part of the concrete compared to the bottom part of the concrete. So at the time of concreting, the excess water added to improve the workability. Also, some air voids will be there in the concrete mix. So due to vibration, this less dense water and air will try to go up, and the high dense material like cement, sand, and aggregate will settle down. So that it will create more voids in the top part of the concrete and less voids at the bottom part of the concrete. When we have the rebar at the top part of the concrete, this moving water and air will get trapped under the horizontal bar, which will disturb the bond strength of the rebar. So, to account this, the IRC 112 provided a factor of 1.43 and they are calling it as an unfavorable bond condition. So, all the vertical bars placed parallel to the gravity or the concreting we can consider as a favorable bond condition. As shown in this figure, all the green color bars are favorable bond condition and all the red color bars are unfavorable bond condition. When bar is positioned in vertical direction, the less chance to water and air get trapped under the bar, so it can develop a very good bond with the surrounding concrete, so we can consider it as the good favorable bond condition. When the bar is placed horizontal, that we should be considered as an unfavorable bond condition. As we seen in this image, the more whites are top part of the concrete element and less whites and bottom part of the concrete element. When the total thickness of the element is less than 250 mm, then all the bar we can consider as a favorable bond condition. Since in this example I assumed as a 1 meter depth, so the 250 mm zone bars provided within this bottommost 250 mm zone, we can consider it as a favorable bond condition. Rest all other bars we should consider as a unfavorable bond condition. So these values are calculated for the 20 mm diameter bar and M35 grade concrete and Fe500 deformed bar. So as per IS 456, in IS 456 they have given separate bond strength for the bar in compression and bar in tension. Whereas in IRC 112 they didn't given a separate bond condition based on the nature of the force or the bar provided in whether the compression zone or tension zone. But in IRC 112 they have taken up that top bar effect into consideration by providing the 1.43 factor for the unfavorable bond condition, which is not considered in IS 456. Comparing this value, this all value calculated for the 20 mm diameter bar In tension nature, this is for compression and this is for tension and this is for favorable and unfavorable condition. By seeing all these value, this IRC 112 value is a better development length than this IS 456 since they have considered the top bar effect into account. All these values calculated by assuming 20 diameter bar and M35 grade concrete and Fe 500 deformed bar. In IS 456 we have different bond conditions for the reinforcement provided in tension zone and reinforcement provided in the compression zone of the RCC element. Whereas in IRC 112 we don't have that differentiation of compression or tension, but we have the favorable unfavorable bond conditions which is not discussed in IS 456. By seeing all these values, since these favorable unfavorable bond consideration taken into account in IRC 112, so we have more development length in IRC as per IRC 112 compared to IS 456. Why bond length is more important? So let's consider this point. So right side to this point is presented with the yield strength and left side is with the development bond strength. So let's take consider a 20 diameter bar. The 20 diameter bar can take 136.7 kilonewton before it start yielding. So to get the sufficient bond length, so we should have at least 800 development length for the 20 diameter bar. So by mistake, if I provide only 500 development length, then this 500 development length can create a bond strength of 85.5 kilonewton, which is even less than 60 diameter bars yield capacity. So even though we have done a very accurate design, if you did a small error in detailing, which leads to early failure, that too as we discussed, this bond failure will be brittle in nature, so it will not give any warning or cracks or deflection even before it start fail. Once the load is reached 85.5 kilonewton, this concrete will fail in bonding. This bar will be pulled out, the structure will collapse immediately.